Okay, welcome back to class. The plan for today is to continue with chapter 6. We started talking about continuous probability distributions last time. So today we're just going to um, kind of review some of the basics of that and then move on to the uniform distribution and the standard normal distribution. So I'm going to pop a table in chat here. I think I shared this last time, but um, just so you have quick access to it, I popped a PDF in chat for the standard normal table, which we will be using a little bit later this class. But we're going to start out with just some quick discussion of just kind of reviewing some of the basics from last time, and a quick discussion of uniform distribution is where we'll start. The quote of the day today is from Nietzsche, the philosopher, early 1900s or so, German philosopher. And in his book Beyond Good and Evil, it's kind of uh, at least there's a couple of sections that are just like a bunch of little aphorisms, or like little, short couple of sentence statements. And I think this one's a pretty famous one. Whoever fights monsters should see to it that in the process he does not become a monster. And if you gaze long enough into the abyss will gaze back into you. Um, and there's a similar kind of notion, I think, expressed in the Silmarillion, the uh, kind of, I guess, prequel to the Lord of the Rings and Hobbit series, kind of like the world building, explanation for Middle Earth. Um, there's a statement in there that for those who will defend authority against rebellion must not themselves rebel. Um, so I think just, good words of wisdom that oftentimes if uh, we're fighting against some idea or something, we become so caught up in the fight against that idea, we kind of lose track of the reason that we started that fight in the first place, and the reason that we took the stance we took in the first place, and maybe even become the thing that we're fighting against in the process of fighting against it. So, okay, so chapter 6, we are switching gears to continuous probability distributions, and we saw that, there's some strange phenomena that come out of that switch. So if we recall really quickly the basics of our discrete probability distributions, we have a probability distribution here that has different outcomes, x1, x2, x3, along with probabilities. And in the terminology of chapter 6, we call this a probability mass function, PMF. Our outcomes we kind of think of as locations on an axis, and our probabilities we think of as point masses at those locations. And then our expected value, or our mean, really just equates to the center of mass of the distribution. And we showed how we can take a discrete probability distribution and kind of, slice it up into, say, smaller and smaller bins. So our bins get thinner and we get more bins over time. And in the limit, we get a continuous distribution. These distributions are represented by graphs, but these graphs represent probability density, not probability anymore, but probability density. And a density across in this case, say linear distance, gives a mass. So probabilities correspond to areas under the PDF, accumulation of density across kind of the x-axis across distance. And we also mentioned that meaningful events in the continuous world are intervals. So for instance, probability x bigger than A, probability x less than B, or probability x between A and B would be interesting events to talk about, but say probability x equals number, well, that probability is always going to be 0. Note that it's very different in the discrete world, where we have probabilities of specific outcomes. Probability x equals x1 is most likely not going to be 0. But in the continuous world, anytime we see probability x equals number, that probability is 0, because we're accumulating a density across 0 width, right? X's interval starts at, in this case, 6 feet tall and ends at exactly the same place. So we have kind of a height times a width of 0, giving me 0 area, 0 probability. And recall that the requirements for a function to be a PDF very similar to the requirements to be a PMF. It has to be non-negative everywhere and have total area 1. So we talked quite a bit more about this last time, building this up. So let's look at an example. We're going to look at the uniform distribution, probably the simplest continuous distribution that we can actually take a look at. So here we might say that x is uniform on the interval a to b. So this brackets AB indicates the closed interval a to b on the real line. So I have interval a to b here. And the uniform distribution just says that we have constant probability density on this interval a to b. So let's say we have a y-axis here, and our function is height c on the interval a to b, and 0 otherwise. So we do have a piecewise defined function, but it's not too terribly complicated. Note that the total area under this curve, well, to the left of A or to the right of B contributes no area. And under the curve here, we have a rectangle of width B minus A and of height C. So the total area would be C times B minus A. But we remember that the total area is constrained to be 1. We want 100% total probability. And that means that C, the height, has to be 1 over B minus A. So if I set A and B, I pick A to be 1 and B to be 5, the height has to be, say, 1/4. So C has to be 1 over B minus A in order to make this rectangle have area 1. So let's take a look at a specific example here. Let's suppose that a certain train arrives every 15 minutes. So, you know, the T or the trolley, something like that. But we don't know when it last arrived at the station. We don't know what the schedule is. We just know that it comes every 15 minutes. So we walk up to the platform and the train's not there. We know we're going to have to wait some time. We choose to model the amount of time that we have to wait as x, a uniform random variable in the interval 0 to 15. Right? We might have walked onto the platform just as the train left and pulled around the corner and we couldn't see it anymore, or we might have walked up just as the train's about to come around the corner and come back to us, or maybe somewhere in the middle there. So we're going to say that it's equally likely that we have to wait any time from 0 to 15 minutes. And let's compute the following. Oh, let me clean these up. I have some of these answers typed in here. There we go. So let's compute the following. Let's start with an easy one, probability x less than 15. So our distribution is going to be the same for all of these. So it's on the interval 0 to 15. We have a uniform distribution. Usually I draw it a little quicker and a little more sloppy, but I plan to use this for several of these problems, so I'm drawing it a little nicer. And we know that we have to have height from up here, 1 over B minus A, or this height has to be 1 over 15. So that this entire rectangular area under the PDF, under this blue curve, that's this, that, and this piece over there, but I'll just indicate the interesting part. So the entire area under the PDF is 1/15 times 15 minus 0, or that is just 1. So what's the probability x less than 15? If I'm asking what's the probability that I am to the left of this vertical line, well, remember, probabilities are represented by areas, that's this area. What is that area? Well, that area to the left of 0 gives me 0 area, and between 0 and 15 gives me 15 times 1/15, or 1. If the train arrives every 15 minutes, what's the probability I have to wait less than 15 minutes? 100%. As I guess a little side note, what's the probability x less than or equal to 15? Well, that's also 1. Well, why is that? I guess that's because probability x less than or equal to 15 is probability x less than 15 plus probability x equals 15. But remember, when we're in a continuous distribution, probability x equals number is always 0. Because we've effectively sliced that bin to the point where it's infinitesimally wide, there's no frequency left in there. So this bit is 0. When we're in continuous distributions, we typically don't really worry about whether we include or exclude the boundary of an interval. Now, very importantly, when we're in discrete distributions, it's quite important, right? If I ask what's the probability I roll a number less than 2 versus less than or equal to 2, those are two very different questions with two very different answers. But if I ask what's the probability I wait less than 15 minutes versus probability I wait less than or equal to 15 minutes in the continuous world, that's the same answer. Because the probability I wait exactly 15 minutes in a continuous distribution is 0. And we see that this is a certainty, it's a 100% chance. And of course, that's because a train arrives every 15 minutes. So of course, I'm going to wait less than or equal to 15 minutes. Now, it is worth just kind of reminding ourselves that we're in the mathematical world here. We're discussing a mathematical model and its properties. So, you might say, well, if I actually physically, walked up to the T stop at the end of Hut Meadow Bridge and stood there, and I know that the T is scheduled to arrive every 15 minutes. I mean, there's some chance that I have to wait longer than that, right? Maybe the thing breaks down or, has a problem or gets held up at another train station for some reason. Maybe it's running a little bit late, right? So in the real world, maybe I would have to wait 15 minutes on more than 15 minutes on occasion. But again, under our model, it's a certainty that we'll wait no longer than 15 minutes. That discrepancy is an issue of applying our model to the real world, right? That's a shortcoming of our model in interpreting the real world. There are some things that a model that's simple might not take into account that are real world factors. Okay, so what about the probability that x is between, say, 3 and 5? Well, here I'm looking at from 3 to 5. You know what I'm going to do, actually? Let me do this really quickly so that I don't have to either keep erasing with the eraser or keep undoing. I'm going to make, did that work? Okay, that didn't do what I thought it was going to do. Let me do this a little differently then. I'm going to take a screen capture of this so that I can just keep this and erase on top of it. There we go. I didn't think of doing that in past semesters, and it just occurred to me that I could do this, and then it'll make it easier for me to erase things. So, all right, here's my PDF. So probability x is between 3 and 5. So that probability is going to be represented by this area here. Well, I see this area is a rectangle, nicely enough. Basic geometry, I can compute the area of this rectangle as the base width, or 5 minus 3, or 2, times the height of 115. So what's the probability x between 3 and 5? What's the probability I have to wait between 3 and 5 minutes? 2/15. Now, an interesting characteristic about the uniform distribution is if I looked at any interval of width 2, what's the probability I have to wait between 7 and 9 minutes, or probability I have to wait between 11 and 13 minutes, or between 0 and 2 minutes? These are all intervals of width 2. I get the exact same answer. So a characterization of the uniform distribution is that the probability of an event is only dependent on the size of that event's interval. These are all intervals of width 2. So they all get probability 2/15. Or another way of thinking about it is if I took this block here, or these two vertical, this kind of vertical column, and I shifted it left or right, as long as the width of that vertical column stayed the same, whether it's over here or whether it's over here, I didn't draw that one very well, but it's going to be the same area. Now, if I had a PDF that, wiggled around a little bit, when it's here, it's going to be a higher area. And when it shifts over here, it's going to be a lower area, right? So this is a characteristic of the uniform distribution, that it's independent of location. The probability is independent of location, only dependent on the size of the interval that we're discussing. Now, there is one small caveat to that. If I say, what's the probability that, let's say 14 less than x less than 16, well, hey, that's an interval of width 2. But, and here's where I can nicely just, fingers crossed, erase, and my PDF stays and my markings disappear. So proud of myself for thinking of that in the morning. Usually I'm a little more awake in the afternoon than the morning. But so what about the probability that we wait between 14 and 16 minutes? Well, here's 14, but here's actually 16. So kind of like half of my interval is outside of the window of possibility, right? This would only be 115. Because this bit is only of width 1 and height 1/15. This bit is of width 1 but height 0. So we get like 1 times 1/15 plus 1 times 0. Right? This is probability 14 less than x less than 15, plus probability 15 less than x less than 16. Not really worrying about probability x equals 15, because again, that probability is going to be 0. So these two events don't technically combine to make this, but this equal sign is still valid because the only thing that I've excluded is something that has probability 0. So these are still exactly equal to one another under the probability sign, even though the two events themselves are slightly different at one point. And now we can see that this is kind of the bit where the interval width, probability being proportional to the interval width, does hold. That's 1 times 1/15. And this bit is kind of outside of the interval a to b, so it contributes an interval width of 1, but a height of 0 contributes 0 probability. So we do have to be a little bit cognizant of that, right? But as long as my interval falls fully within 0 to 15, then the probability is only dependent on the interval width and not the interval location. Any questions so far? So that's probability x between two numbers. We could also have a question like, say, probability x less than 5, or probability x bigger than 10, something like that. Probability x less than 5. Well, x less than 5 goes all the way off to the left. But note that this entire contribution to the probability to the left of 0, what has 0 height? So whatever its width is, if I look at a block of width 100 or 1,000 or a million, multiplied by actual 0 gives me 0. So I get 0 contribution to the probability from over here. And the real contribution that I get to the probability x less than 5 is this block here. This block has interval width 5 and height 1/15. So we get 5 times 1/15 or 5/15, or that's 1/3, say about 33%. So a third of the time, or about 33% of the time, we'll walk up to the train station and we'll wait less than 5 minutes. The train might be just coming around the corner, it might be a couple minutes away, but a third of the time we'll wait less than 5 minutes. What about probability x bigger than 10? Well, pretty similar here. This block here contributes to our probability, and this block here just contributes a big 0 to our probability. We can never wait more than 15 minutes under this model. So the probability of waiting more than 15 minutes is 0. But the probability of waiting between 10 and 15 minutes, that's an interval width 5, height 1/15. It has that same interval width. We get the same probability. I remember that the interval width is what gives our probability. In this case, we don't see the interval width directly in our probability statement, but we see it kind of implicitly through the graph, through the fact that we're kind of chopping off anything less than 0 or bigger than 15, because those are just regions of 0 probability density. We don't accumulate any probability out in those regions. Or put a little more formally, because probability x bigger than 10 is probability that x is between 10 and 15 plus probability x bigger than 15. Here again, I'm not being super worried about x equals 15. And I know that it's an impossibility for my random variable to be bigger than 15. That would be like rolling a standard six-sided die and getting an 8. We say that's a 0 probability, actual 0, not just unlikely, but impossible. And we say the same thing here. Just because it's a continuous distribution or because it's defined on the entire real line doesn't really change much at all. So this is like an infinitely long tail going off to the right here, but it has 0 height the entire time. So the probability is 0. Right. So in this case, the event waiting for more than 10 minutes is equivalent to the event waiting between 10 and 15 minutes. Or, if you want to kind of, if this is seeming a little bit abstract, think of rolling a die. If I said, what's the probability you roll a number, say, bigger than 4, or let's say bigger than or equal to 4, you could just say that's the probability of rolling a 4, 5, or 6. And that would be perfectly reasonable. You don't have to address rolling a 7 or an 8 or a 12 or a 20, even though those numbers are bigger than 4, they're impossibilities under the model. And kind of similarly, what's the probability x bigger than 20? Well, here we have 20, and we're going this direction. What's the probability we wait more than 20 minutes? It's impossible. It's 0. And we could also ask, what's the expected value? Yeah, I really wish I had thought of this several semesters ago. It makes it so much easier if I just have a picture to work off of. So what's the expected value? Remember, the expected value is like the balance point in a probability mass function. When I have my little masses all lined up at their locations, I can find a balance point, and that's the expected value. Maybe say it's there in this case. Well, when I have a function like this, a PDF, this represents probability density, but this kind of whole thing here, this whole thing would represent like a big mass. Oh. So where's my balance point? Well, my mass, I have equal density or equal thickness or whatever you want to call it, the whole way across from 0 to 15. My balance point should be right in the middle by symmetry. I have a nice symmetric situation. My mean should be right in the middle. 0 plus 15 over 2 is 7.5. On average, I should wait 7.5 minutes. I also kind of note that my median is 7.5 minutes, right? There's 50% area to the left of 7.5, 50% area to the right of 7.5, nice and symmetric distribution. So my mean and median are the same. So about half the time I'll wait less than 7.5 minutes, about half the time I'll wait more than 7.5 minutes for the train. Okay. And kind of a side note, the expected value, how do we define it up here? It was like take each outcome and multiply it by its probability and then add those together. So if I take my outcomes, my x's in this case, my linear coordinates, the values along this axis, multiply it by probability density, f of x, to get, in this case, x over b minus a, and then find the area of that function, kind of adding up area going across or accumulating in that area from a to b. That's how we can find the expected value of x, and we would turn out that it's a plus b over 2. We could also find the expected value of x squared, which would be the area under the function equals the area under the function x squared f of x from a to b. This is not as easy of a calculation to do, not by any means. But if we went through some of this and found the variance and so on, I think if I remember right, the variance is b minus a all squared over 12. So I think the variance is b minus a all squared over 12. Pretty sure I remember that right. So kind of a strange formula for variance, but you can see the wider the interval from a to b, the larger the variance, as we'd expect. If my train arrives every 15 minutes and I have an interval 0 to 15 versus if a different train arrives every hour and I have an interval from 0 to 60, when I walk up to the platform, my the range of expectations, let's say, the range of reasonable possibilities is much greater for the train that arrives once an hour than for the train that arrives every 15 minutes. Okay, any questions about the uniform distribution? So let's move on to discussing the normal distribution. The uniform distribution, we talked about it. It's a nice distribution. It's very useful in practice. In fact, it's a great distribution to use when all that I know is an upper and a lower bound. So if, like in this kind of example, where all that I know is that the train arrives every 15 minutes, that I know that there's an upper bound of 15 and of course a lower bound of 0. I can't wait for less than 0 minutes. If I know an upper and a lower bound, this is in some sense the most sensible distribution to use. So it is a good distribution. It's nice and simple, and then I can get answers to probability questions by just evaluating geometry. So that's super nice. But the downside is that it's somewhat restricted in its use. Uh, the places that it is used, it's very nice to use, but maybe those situations don't come up all that often. So let's take a look at a different distribution. And unfortunately, we're kind of jumping to the other end of the spectrum as far as kind of the niceness of the geometry. So we're going to look at the normal distribution. If we remember back in chapter 2, we talked about some characteristics of the, say, bell-shaped curve, the normal distribution, the Gaussian distribution. And it had 3 characteristics. It was symmetric about the mean, it peaked in the middle, and it tails off to both sides. Oh, my pen is being super glitchy today. There we go. Okay, so let's recall what this distribution looked like. So it looks kind of like this. And here I think I'm going to do my same trick that I did above and maybe screen cap it. Oh, I didn't not want to do that. All right. So here I have the mean in the middle. I'm symmetric about the mean. So if I were to pick this graph up, flip it over and lay it back down, flip it over the mean and lay it back down, it looks the same. It has a peak in the middle, and it tails off to both sides. So there's a function that gives rise to this picture, and this is what this function is. It's an exponential function. Kind of the heart of it here is it's like e to the minus x squared. It has a couple of other attributes. The mu, this x minus mu, says, well, e to the minus x squared is like humped around 0. Changing x to x minus mu gives us a shift to the right of mu units. So that makes us center around mu, around the desired mean. And then this over 2 sigma squared, that allows us to set the variance or the standard deviation for the distribution. So the normal distribution has 2 parameters, mu and sigma, the mean, and the standard deviation. This is kind of similar to how like the Poisson distribution has 1 parameter rate lambda, or the binomial distribution has 2 parameters, n and p. So if I looked at a binomial distribution with n equals 5 and p equals 1/2, that's a different distribution than n equals 10 and p equals 2/3, but they're in the same family of distributions. They have underlying characteristics that they share, and then I can tune those parameters to match the particular problem that I'm looking to solve. And it's a similar idea here. So I have 2 parameters, mu and sigma, and these set the center location, the mean, as well as the standard deviation out here. These points are called inflection points, where we kind of go from curving up to curving down to curving up. When we kind of change curvature from up to down or down to up, we call those inflection points. And these inflection points are 1 standard deviation away. Mu plus sigma and mu minus sigma. So sigma is kind of what's sometimes called the shape parameter, or it stretches the distribution sideways or compresses it sideways. And mu is the location parameter. If I change mu, I just take the whole distribution, I shift it left or right. Okay, a few notes on this. Note that the symmetry implies that the mean, the median, and the mode are all equal. So the median, the 50th percentile, is going to be right in the middle. And the mode, the most frequently occurring data value, we have this peak in the middle. So the mode is also in the middle. This is defined for all real numbers x. That was kind of built into our requirements for a function to be a PDF. Some people don't like defining these PDFs for all real numbers x, and they only define them for all real x when they need to, but we're taking this approach. But we look at this and we might say, well, some of the things that I'm going to want to use the normal distribution for, things like maybe modeling people's heights, right? We talked about how maybe the heights of people after you stratify based on sex, they might follow a normal distribution. Things that are kind of combinations of lots of small influences tend to follow normal distributions. Well, if I'm modeling a person's height with this, I mean, if it goes off to infinity on both sides, I'm going to be claiming that there's some probability that they're more than 10 feet tall. It's going to be a small probability, but it's non-zero. Or even I'm going to be claiming there's some probability, some positive probability they're less than 0 feet tall. That doesn't even make sense to say. Well, I think it's important to realize that we're working in the mathematical model space here. And when we overlay this onto a real world phenomenon that we're trying to understand better, we need to keep in mind that all models are wrong, but some are useful. And in practice, in the normal distribution, these tails go to 0 extremely fast. So for something like heights, the chance that somebody's going to be, estimated to be, say, over 8 feet tall or maybe under like 3 feet tall for, say, an adult is going to be so close to 0 that you really can't tell the difference between it and 0. And by the time we get down to the probability that somebody is going to be a negative height, which is nonsense, but if the probability is like 10 to the negative 50 power, like nobody really cares about that from a modeling standpoint. It's not going to affect any of our predictions or any of our understandings really at all, unless we really take this model to the absolute extreme and try to pretend that the model is reality or something like that. But these tails go to 0. They don't just, it doesn't just tail off to both sides, but these tails go to 0 very, very fast. And we'll actually see it coming up in chapters 7 and 8 that these tails go to 0 so fast that in some kind of loose sense, it can sometimes cause problems, and we have to use a different distribution uh, to evaluate certain problems, where the tails, a distribution that looks kind of like the normal distribution, but the tails don't go to 0 quite so fast. And then again, just a reminder, probabilities are represented by areas. So asking what's the probability that somebody's between these two heights, that probability would be represented by this area. Now I have a little bit of a problem here, and we're going to explore this in much more detail in a few minutes here, but my problem is that this is a pretty darn complicated function that gives rise to this curve, and I need to figure out areas under the curve. I mean, when I had a nice function like a constant function, I could find areas under the curve really easily because they were just rectangles, and I could do base times height, and that gives me area, that gives me probability. Even if I had something, I don't know, that was maybe like say a triangular distribution, I could still find areas here. That's just a trapezoid. I could use geometry to work that out. Perhaps, perhaps if I had a distribution that was like I don't know, maybe a semicircle, I might be able to work out an area like this by taking, say, like a circular segment minus a triangle or something. I might be able to use geometry there as well. Oops. So if I had a nicer geometric structure that I was working with for my function, I might still be able to use to leverage the geometry that I know to find the areas. But how the heck do I find an area like this? And a little bit of the answer is calculus. We can find areas under curves that don't have flat sides, where the side is rounded like this, using some calculus techniques. But it actually turns out that this function is so complicated that even with calculus techniques, we can't figure out the exact area. So what's the actual answer? Essentially, the actual answer is computer approximation. We kind of take an area like this. We say this is the area I'm interested in. Well, what do? I make a whole bunch of little subintervals, a whole bunch of little bins, basically. I basically treat it like a probability mass function. And I approximate this curve by all these little bins and their areas. And then I add those areas together. And when that's done, what does that result in? Well, it results in a table of values. So again, I'm going to, just in case anybody came in a little bit late, I'm going to post the standard normal table in chat. Let me do that really quick here. Okay. So you have that available. And that's exactly what this table does. It gives us a list of, oh, let me get my windows sorted back out here. Okay. So what that table does is it gives us a list of some specific areas and their associated or some specific areas and their values. So we'll see how to use that table in a few minutes. But because probabilities are represented by areas, and because this is a complicated curve, the normal distribution, we really need to use a table like this, or we could maybe use a calculator or Excel or something, which more or less just has these tables stored in them and will give you an answer based on something that's more or less like one of those tables. So we're not going to be able to compute these areas by hand like we were able to for the uniform distribution. We'll be using a table instead. And then I also want to discuss quickly, what's the effect of changing mu or sigma? So if I look at my kind of baseline normal here with a certain mean, what color did I make it up here? Green. This has a certain mean and a certain standard deviation. I'll try to make it somewhat symmetric on the two sides. What happens if I change mu? What happens if I say increase mu? Well, that would just take my center of my distribution and push it to the right. So I would have the same looking distribution, just with mu over to the right. I just shift my whole distribution to the right a little bit if mu were to increase. Or if mu were to decrease, I would just shift to the left. So mu is my location parameter. If I change it, I just change where the center point of my distribution is, but the shape of my distribution stays the same. Now, what if sigma were to, say, increase? Well, that means that these inflection points are getting pulled further out. So maybe my new, say, mu plus sigma and mu minus sigma is out here. Well, that means that kind of outcomes or events that are far away from the mean are a little more likely to happen, right? That makes sense because the standard deviation is increased. That makes sense because the width of my distribution is increased. Well, so now my inflection point, let me try to draw this somewhat carefully, is going to be a little further out here. I'm pushing the whole distribution, I'm kind of stretching it left to right. But now if I try to do something like this, right? Well, now I have more area under the curve than I originally had. My area under the curve has to be 1. So if I gained area in the tails, then I must lose area in the center here. So my distribution is kind of wider but shorter. Let me redraw that middle so it looks a little more symmetric. So my distribution got wider from increasing the standard deviation, but then to compensate for that, it had to get shorter. Or if sigma goes up, this constant in front here, that's the constant multiple that affects the height of the distribution. And it makes it's the thing that we need to multiply this thing that's really doing the work of making the curve. We have to multiply by this 1 over sigma times square root of 2 pi. We got to multiply by that to make sure that the area under the curve is 1. And I see that sigma is in the bottom. So the sigma increases, that height factor decreases. So I have a wider and shorter or squatter distribution. As a little side note, we would call this platykurtic. So platy, like platypus, like flat, and cortos, meaning humped. So like flat humped. It's a little flatter. The hump is a little flatter. And if we went the other direction, it made sigma smaller. So now I want my inflection points to be in here. Well, this is going to be skinnier. So it's going to look like this. I've lost area in the tails, but I still need to have a total area of 1. I need to compensate by having more area near the mean over here. So if sigma decreases, I tighten up my interval. It kind of squeezes in. I have more of a concentration of area near the mean, which is what I'd expect for a lower standard deviation. But also my peak is taller. It's a pointier peak because I've got to compensate for that area. I've lost some area in the tails. Events out in the tails or far away from the mean are less likely, so things near the mean should be more likely. We call this leptokurtic. So if I increase or decrease sigma, that's how things change. If I increase or decrease the mean, then I just shift my distribution left or right. And I have this all-important idea of the standard normal distribution. And it typically gets the trademarked variable z. If you see a z floating around in statistics or probability or stats, that almost always means standard normal distribution, unless the context is made very clear otherwise. And the standard normal distribution is the normal distribution. Remember these normal distributions is a family of distributions. I can pick a different mean and a different standard deviation. I get a different curve, but I can pluck one member out of that family to be kind of a representative member. We call that the standard normal distribution with a mean of 0 and a standard deviation of 1. So these inflection points are at 1 and -1, and the center right at 0. So that is our standard normal distribution. Okay, so let me bring up my standard normal table and switch my share here. Give me 1 second to get that put together. Okay, so we see that we have our, zoom out one and click on this. Okay, there we go. We see we have our standard normal distribution table here. There are 2 sides to this, 2 pages to it, positive z-scores and negative z-score sides. And we see this gives us areas to the left under a standard normal distribution with mean 0. So this table, like I said, I posted it in chat. It's also available on Blackboard in the chapter 6 folder. So if you if you lose track of it, you can always go to Blackboard and get it. It's also, of course, in the book. You can see this one I downloaded from the book 10 years ago. They've made it since then they've made it harder to like copy pages out of the book, unfortunately. So I wish they would just make these tables available for like free downloads, but I don't think they do. So that's why this one, is watermarked from 10 years ago, because it was easier to copy pages out of the book back then. But that way, if you want to have easy access to this just in one file or something, you can use that file. Okay, so let's just look at a bunch of different events on a standard normal distribution. So we're using Z here. Like I said, that's kind of trademarked as a standard normal. And we have a bunch of different events. These events are intervals, like probably Z less than a number, probably Z greater than a number, probably Z is between 2 numbers, and so on. Let's just start working through a bunch of these different problems and see how this table works. So I probably will shrink this over to the side a little bit so we can see a little more of the table. And if I'm looking at probability Z less than 0, I always like to draw a picture with these. Even when you get pretty comfortable with doing them, it's still a pretty good idea to draw a picture. It just kind of helps you to keep your bearings on the problem. Okay. So here we have mean 0, standard deviation 1. And I'm actually going to screen cap this and then paste it so that we can use it later on. We can just copy it over and over. Okay, so probability Z less than 0, this is a graph of the PDF of Z, my standard normal distribution. And I'm interested in the event Z less than 0. So I'm interested in knowing this area, the area to the left of 0. In this case, I actually don't even need my table. I know that my distribution is symmetric, so its mean and median are the point of symmetry, or its median has to be 0. Its 50th percentile is 0, which means the area to the left has to be 50%. This is basically the one and only number that I can just get exactly an exact answer for my normal distribution. The area to the left of the mean is going to be 50%, and also the area to the right of the mean is going to be 50%, and the area under the whole thing is going to be 100%. Other than those three special cases, I have to use my table. So what about probability z less than 1? So here I'm looking at z equals 1, and I want the area to the left of that. Now, nicely enough, my table does give me areas to the left for a standard normal distribution, so that's good. Now, my first page here gives me negative z-scores. In other words, I'm looking for areas that are to the left of a number that's less than 0, but my problem has a positive z-score. I'm looking for the area to the left of a number that is bigger than 0. Right, this picture up here doesn't look too close to the picture that I have written over here. But if I go to the positive z-score side, I'm still looking at areas to the left. But in this case, areas to the left of a positive z-score, of a positive number. So like the area to the left of positive 1. Okay, so I need to use this table somehow to get my answer. And if I look in the top left of my table here, that's a little z. So that's telling me that my leftmost column and my top row are index column and row. So this is getting my z accurate to the 10th place, so the digit in the 10th place. And then I would refine that by going across the column and getting the 100th place. So on the outside of my table, this row and this column are z index. These are numbers like this 1 or this 0 here. In the middle of my table, or what I often call the field, the middle of the table in here, these are probabilities or these are areas. So if I want the probability z less than 1, if I want the area to the left of the z-score of 1, we'll note that 1 is 1.00, of course, 1 unit, 0 tenths, and 0 hundredths. So I come down to 1.0, getting the digit in the tenths place accurate. And then I zero in on the hundredths. I also want 0 hundredths. And I look at the intersection of my 0 hundredths column with my 1.0 tenths column, or sorry, tenths row. And I see that the intersection of that column and that row, 1.00 for the index on the outside, the intersection in the table gives me 0.8413. That is the area to the left of 1 on a standard normal distribution. Or the probability z less than 1 is about 84.13%. So that's how I use my table. We're going to go through lots of examples. So we'll see, we'll get a lot of practice doing this. We'll see how to do different variations of probabilities. Like what if I have a right tail area, but my table gives me left tail areas? How do I handle that, right? So we'll talk about several different possibilities, and we'll get a decent bit of practice going through this table. So if you didn't catch that the first time around, we'll have several more opportunities too. But the biggest things to remember are the first row and the leftmost column are z indices. These are our z numbers. These are our numbers that are like on the axis down here. And these numbers that are in the field here are all probabilities or areas that are associated with areas to the left of those z-index numbers. As a side note, note that essentially all of these are rounded with the exception of this one here. 0.5000, the area to the left of a z-score of 0.00. That was what we found up here. That was exactly 50%. But other than that, one result here, every other one of these is rounded. I'm not going to rate approximately equal to all the time because kind of from this point forward, we're essentially always going to be approximating or rounding things. So I'm not going to be super careful about writing exactly equal to versus approximately equal to. But from this point forward in our coursework, pretty much everything is going to be rounded. So this table, these probabilities are accurate to 4 decimal places. You know, there are some other tables that only have 3 decimal places of accuracy or 5 decimal places of accuracy. But if you use this table, this should give you the right amount of accuracy for, you know, all of the MyStatLab questions, that kind of thing. So that's another little point that I want to mention. If you, you know, plug a question into Excel or into your calculator or something, you might have to round it. You know, your Excel or your calculator might give you more decimal places of accuracy than we get here. And the question might be asking you to round to 3 or 4 decimal places of accuracy. Okay. I'm like quite pleased with myself that I thought to do this, so I don't have to rewrite one of these every time. So we looked at probability z less than 0, probability z less than 1. Similar question, probability z less than -2. So here I'm looking for, here's -1, here's say -2. I'm looking for this area in this left-hand tail. Now, something that's really nice about drawing the picture beforehand is I can just look at the picture and I can see, okay, this should be 50%. I can kind of just tell that looking at the picture. I can tell that this area should be bigger than 50%. Is the answer we got in line with that? Yes, it is. This gives me a reasonability check. I can look at this area and say, well, the whole area to the left of 0 is 50%. This little tail area here to the left of -2, that should be like a lot less than 50%. I'm going to get an answer, and I can have something to check my answer against now. So what's probability z less than -2? I am on a standard normal distribution, so I do want to use my standard normal table. But -2 is a negative z-score. I need to use my other page. So let me jump back to my negative z-scores page. And yes, this picture does look more in line with the picture that I have for this problem, right? Where the positive z-scores looked more like the picture I had for the last problem. So I'm on my negative z-scores page. I'm on the correct page. That picture looks right. That's always a nice little check. If you've drawn a picture, check that the pictures look kind of concordant with one another. And then I want z less than -2. Well, of course, -2 is -2.00. So that's -2.0 getting accurate to the 10th place and then 0 hundredths. So here's my -2.0 column. Sorry, -2.0 row from the index column. So I know that my answer is going to be one of these probabilities here from 0.0228 up to 0.0183. It's going to be one of those. I also need 0 hundredths because -2 is -2.00. So I also need this first column. And the intersection of my -2.0 row with my 0 hundredths column gives me a probability or an area of 0.0228. Or that's 2.28%. Is that a lot less than 50%? Yes, it is. It's a small probability, definitely less than 50%, but a lot less than 50%. That does mesh with what I expected. So I'm pretty confident in the answer. Any questions so far? Okay, let's look at probability z less than 0.347. So 0.347, somewhere between 0 and 1. I'm not going to be super worried about getting it, really, really precise. But I'm looking for this area. I know the area to the left of 0 is 50%, and then I have a little more area on top of that. So this should be bigger than 50%, but not a ton bigger. It shouldn't be like 98%, right? It should be like a little bigger than 50%, maybe 60%, maybe 70%, but not like 99%, but definitely should be bigger than 50. So probability z less than a positive number. This is a left tail area. The area is going off to the left. But I want the area to the left of a positive number. I've got to use the other page of my table. This gives me areas to the left of negative numbers. This gives me small areas. I need a bigger area. And again, here I get area to the left of positive z indices, and my picture meshes more nicely with my picture that I have for my problem than the picture on the other table. So that's always a nice little kind of secondary check is, does the picture displayed on the table look like the picture that I drew for my problem? Now here I have a little bit of an issue. I want probably z less than 0.347. I have all the way out to a thousandths place, but my table is only accurate to z indices that are to the hundredths place. Well, I've got a round. So this is approximately probability z less than 0.35. 0.347 rounded to the hundredths place, rounds up to 0.35. And now I can go to my z index column and look for 0.3, which is that row. I know my answer is going to be somewhere in this row. And then I want 5 hundredths. And I see where those two intersect is right here at 0.6368. So that's in the 0.3 row and the 0.05 column to make 0.35 for my indices. They come together in the middle of the table, the middle of the field, and that gives me an area or probability of 0.6368 or 63.68%. That is a number that's bigger than 50% by a little margin. And that's exactly what I expected based on the picture. Any questions so far? All right, let's do one more of this problem type. Probability z less than negative 1.223. So here I know that this inflection point on the left is -1. And we're a little further to the left of that for our boundary line, -1.223. And we're looking for events that are, well, or outcomes. We're looking at an event that is to the left of that. We're looking for outcomes that are to the left of -1.223. So there, we're looking for the area in this tail. When I have a small area, oftentimes I'll kind of point to it with an arrow to highlight it. Sometimes I know it's a little hard to see on your screen, especially when I'm in full screen like this. So that's the only reason I wrote that arrow there, just to highlight where that desired area is, because it's a little small. We can see that it's definitely an area that's less than 50%. The whole area to the left of 0 is 50%, and this excludes some of that area. So it's going to be less area than 50%, and it looks like it should be a lot less than 50%, right? It shouldn't be like 45% or 40%. It should be more like 10% or 5%. So it should be quite a bit less than 50%. Okay, so let's check. Well, we want an area to the left. Well, that's good. But we want an area to the left of a negative z-score. Switch to the other side. Area to the left of a negative z-score. And this picture looks like it's in line with my picture that I've drawn over here. So this is the page that I want to use. And again, my z indices go out to the tenths and then the hundredths place, but not to the thousandths place. So I'll round this to probability z less than negative 1.22. So I'm looking for a z-index that has negative 1.2 for the tenths place. Let me scroll down just a touch here. So looking in my z-index column on the left, I find negative 1.2 is here. So I know my answer is going to be in this row associated with the negative 1.2 tenths place. And then I need negative 1.22, so 2/100ths. I'm looking for this column as well, and I see that the intersection of that row and that column is right here, 0.1112, or 11.12%. Is that in line with what I expected? Yeah, it looks good. It's a number that's a lot less than 50%. That's what I expected. If I had gotten 45%, I'd be skeptical. If I'd gotten more than 60% or something like that, or if I got 65%, I would know that it's wrong and I would have to go back and check my work. Any questions so far? Okay, let's shift gears a little bit. We have a table that gives us areas to the left. That's one of the kind of, events that we might be interested in. Probability z less than some number, but we kind of have two other events that are interesting as well. Probability z greater than a number or probability z between two numbers. How do we handle these? Do we need a new table for each of these? Well, no, we can actually leverage the table we have along with some basic probability understanding to get the answer. So what's probability z bigger than -1? But here is -1. And that's probability z bigger than -1. So my issue is that I would love to come down to here and use a table like this, but these areas point off to the left and this area points off to the right. But I do kind of notice that this area over here kind of qualitatively looks similar to this area over here. They're just pointing in different directions. It's like one is just the mirror image of the other. Or I might think of it this way. I might think that if I look at my negative z-score, I look at this picture and I look at this picture, and if I kind of like smush them together, they would kind of make up all of the area, right? If I added a left tail back in, the left tail that I excluded to the left of -1, that would give me the total area under the curve, which I know is 100%. I can switch a right tail to a left tail in two different ways. One, I could use the symmetry of the distribution, or two, I can use the complementary events rule. So I could use complementary events, and that would look like this. I could say, well, oh, there we go. Okay. So I could look at this and I could say, well, again, I want the area to the right of -1. I can construct that area by taking the whole area under the curve. I don't think I can paste off to the right over here. I think it'll always left align. So I can take the whole area under the curve that includes the left tail that I'm not interested in, as well as the right area that I am interested in. So this includes this area and that area. So here's -1. And then I can just get rid of what I don't want. I can subtract off. There's -1. And what do I want to get rid of to construct this shape on the left? I want to take the whole thing and chop off the stuff to the left of -1. Or in other words, I see that probability z is bigger than -1 equals, well, the whole area under the curve is just 1 minus the probability of the complement. The probability z is less than -1. I do recommend drawing out the pictures here because even though we're kind of just using a straightforward complementary events rule, it can be easy to get some things backwards, especially when we're going to look at using symmetry next. That can be kind of easy to kind of conflate the two ideas and do like half of one idea and half of the other idea and end up with the wrong answer. So I do recommend drawing out the pictures just to keep everything straight. So probability z bigger than -1, the area to the right of -1, which that's kind of the area I want to keep, and I don't have a left tail. That's like the whole area under the curve, the right side and the left side, and then take away that left tail. Or probability z bigger than -1 is 1 minus, well, what's probability z less than -1? Well, that is a left tail. That's something I can look up in my table. I use the complementary event to change a right tail question into a left tail question, and I can look up my left tail answer in my table. This picture, this one over here, does look like that picture on my table, right? I am asking for a left tail area, and it's related to a negative z-score, so I'm looking for the area to the left of -1.00, and that's, of course, 0.1587. So probability z bigger than -1 is 0.8413. So that was using complementary events to solve the problem. We could also use symmetry. So at this point, we've solved the problem. We're done with this problem. We can, but if we wanted to see a different way we could solve it, a different approach we could have taken, on a given problem, you'll typically only take one of the two approaches, whichever one you like the best or suits that problem best. Certainly on an exam, you'd only take one. So don't go through every problem and do both of these. If you want to go through a couple of homework problems and do, each one a couple ways, as a check for your answer to get a little practice, that's fine. But I'm just showing you two different ways to get the solution here. So another approach would be symmetry. And that's leveraging the fact that we know the normal distribution is symmetric about its mean, in this case, 0 for the standard normal distribution. I can flip everything about 0. That would turn a right tail question, a right tail area, into a left tail area. And I can use that symmetry so the shape of the distribution wouldn't change when I flip it over. So I'm looking for the area to the right of -1. That's this area. But again, I can flip this about 0. Both the black curve, this is the distribution, and the area, that's that blue shaded area to the right, My -1 flipping over 0 becomes a +1. And my right tail area, when I flip it about, it becomes a left tail area to the left of +1. Or in other words, I can say that the probability that z is bigger than -1 equals the probability of z is less than. So I change the inequality sign and I change the plus minus sign to a +1. Right. Note kind of how similar this looks to the complementary events rule. We change the inequality to a z less than, but in the complementary events rule, we kept the z index exactly the same, where in our symmetry way of doing it, we change the z index as well. So be really careful. Pick one way to do it, write out the pictures, and then see what that says in terms of the probabilities. If you rush into it, particularly with more complicated problems, it's really easy to, if you rush into it and don't write down the pictures, it's easy to get something, to get the sign of something incorrect, to get a plus where you should have a negative or vice versa, or to get an inequality pointing in the wrong direction. But I noticed that probability z less than 1, this is exactly the kind of question I can answer with my table. I'm looking for an area to the left on a z-score, and that's exactly what I want for my table. So I'm looking for the area to the left of 1.00, or that's 0.8413. Right? Exactly the same answer I got above. I could find this this probability, this area, either way. And I don't think that there's necessarily a better way to do it. I think there are problems like this that it's about the same either way. I mean, maybe you have to do one more calculation up here. You have to do the 1 minus, where you don't have to do it down here, but you have to switch the negative to a positive. So, I think it's really close to equivalent. Which one is more difficult or more effortful or more error prone? I think they're really close to similar to one another. But there are some problems where one way or the other is going to work a lot more nicely. So I think it really does benefit you to kind of have both tools in your toolbox and use the appropriate tool for the appropriate job. And when you have a problem like this, that's pretty straightforward to do, pick the one you like the most. Okay, let's look at probability z bigger than 2. Oh, and I suppose as a side note, I probably should have set up here, my initial impression of this is that the area should be bigger than 50%, but not like really close to 100%. It shouldn't be like 99%. It looks like there's a decent bit missing from the tail there. And I did get an answer that was bigger than 50%, so that's in line with what I expected. So what about probability z bigger than 2? Here's 1 and here is 2. And I'm looking for the area to the right of that. Well, I see that this should be an area that's much smaller than 50%. So I expect to get an answer that's like 5% or 2%, something like that. And again, I can either use complementary events rule or use symmetry. Maybe I'll use symmetry here. And then maybe the next one I'll use complementary events rule. So I know my distribution is symmetric about 0. I'm looking for a right-tailed area to the right of 2, and I'm going to flip everything about 0. So my +2 becomes a -2 when I flip over 0. My right tail area to the right of 2 becomes a left tail area to the left of -2. Or in other words, probability that z is bigger than 2 equals probability z is less than, the inequality sign changes, less than -2, the plus minus on the index changes as well in this case. And again, this is exactly the kind of area that I can look up right off my table, probability z less than -2. That does look like this picture. Everything seems good. Probability z is to the left of -2, and of course -2 is -2.00. That's 0.0228. So a little over 2%. Does that seem right? Yeah. I was expecting an answer a lot less than 50%. That looks right. Then let's look at this one last problem in this subsection. Probability z bigger than 1.735. So here I have 1.735, and I'm looking for the area to the right of that. Again, I know this should be quite a bit less than 50%. So that's the size of answer I'm looking for. And here, instead of using symmetry, I'll use complementary event rule. So I'll say, how can I construct this area? I can construct the desired area, which is a right tail area, by taking the entire area under the function, which includes the area that I want, but also includes a bunch of area that I don't want. And then I can get rid of the area that I don't want. So I can subtract off. Let me put my 0 in here. And my 1.735. So I can subtract off then the area that I don't want. Which is to the left of 1.735. So I make my right tail area to the right of 1.735 by taking the whole area under the curve and getting rid of the stuff to the left of 1.735. Or in other words, probability z bigger than 1.735 is 1. Well, that whole area under the curve is always 100% minus probability z less than 1.735. I think thinking about this geometrically is very helpful, but we see this is also concordant with our algebraic interpretation of the complementary events rule. Z is either going to be bigger than 1.735 or less than 1.735, excluding z equals 1.735, because again, in continuous distributions, that's probability 0. So there's my complementary event. This meshes with the algebraic statement of the complementary events rule. It meshes with the geometry of kind of building up this right tail area by taking the whole area and getting rid of left tail area. And this left tail area is something I can compute off the table. I'm going to round 1.735 to 1.74, rounding to the nearest hundredth. I need to go to my positive z-scores chart, and I'm looking for the row corresponding to a z-index of 1.7 and the column corresponding to a hundredths place of 0.04. And I see that's 0.9591. Now, I might on occasion slip up a little bit, and I've done quite a bit of work here, and I might get 0.9591 and think, oh, maybe that's the answer, right? Maybe forget to subtract it from 1. That's a common mistake to make when we've got a lot of things going on, and if we're not super organized with how we write everything down. But if I thought 0.9591 was the answer, I do my kind of gut check, and I say, wait, I was looking for an answer that's a lot less than 50%, but I got 95%, a lot bigger than 50%. Something went wrong here, right? Then I might realize, oh, wait, I didn't do 1 minus. I need to do that bit. So 1 minus 0.9591 is going to be 0.0409. or 4.09%. That is a lot less than 50%. And so that seems a lot better. Any questions on any of this? Okay, let's move into our next little subsection here. Looking at events where it's like z between two numbers, what's probability that z is between -1 and +1? Now, when I have something like this, if I had just a left tail, I could easily estimate, whether the area is bigger than or less than 50%. If I had something that's just the right tail, same thing. Something like this, I'm not really sure. I have to kind of make maybe a judgment call, like this should be a pretty substantial probability. It should be a pretty good chance. It should be a number that's like 50-ish% in that ballpark. It shouldn't be like 5%, but it also shouldn't be like 95%, right? It looks like it doesn't take up like almost all of the area under the curve visually, but it also doesn't take up like almost no area. I really have to be a little bit more hand wavy with this, at least at this point. So probability z is between -1 and +1. Well, symmetry doesn't help me here. If I flip the thing, it looks exactly the same. But complementary events could help me here. Well, I guess one way to do it would be like to start with the whole distribution and take away these little sides here, but I might even be able to do something a little more efficient than that. I'm looking for areas to the left that I can use to construct this area here. Well, if I took the area to the left of 1, well, again, that includes the area that I want to keep, but it also includes this whole left tail that I want to get rid of. But it does include the whole area that I want to keep between -1 and 1. So here, say -1. But also this left tail area to the left of 1, that's an area I can compute off of my table. So I'm looking to split this area into the sum or difference or whatever of other areas. Number 1, that I can compute off the table, and number 2, that I can kind of easily combine in such a way to make this initial area. So if I take the area to the left of 1, that gives me the area between -1 and 1, but also a bunch of other area in this left tail that I don't want. I need to get rid of that left tail area. Or specifically, what I want to get rid of is the area to the left of -1. In other words, probability z is between -1 and 1 is, well, this area to the left of 1, probability z less than 1, minus probability z less than -1. Be really careful here. It's a little counterintuitive. If you just looked at this probability -1 less than z less than 1, you might be tempted to write this inequality the other way, right? Because it's like in the event, z has to be bigger than -1. But remember, what we're doing is we're getting rid of some outcomes. The outcomes we're getting rid of are those that are less than -1 that don't qualify for the event. So again, going through these couple of pictures, it takes maybe 30 seconds to write out some of the extra pictures and all of that, but I think it's valuable because it really helps you keep straight the plus minus signs as well as the inequality signs. And it's really easy to get those mixed up, right? You get one inequality sign pointing the wrong way, or if this was a positive one instead of a negative one, you're going to get a completely different answer. But I noticed that z less than 1 and z less than -1, these are both left tail events. I can compute their probabilities just based on the table. So what's probability z less than 1? Or I look at this picture and that looks like that one. Probability z to the left of 1.00. That is 0.8413. And probability z less than -1, I got to jump over to the negative z-scores distribution here. Probability z less than -1, the area to the left of, I can barely fit it on the screen here, to the left of -1.00 is 0.1587. And let's just bring Excel up. What? No, it doesn't want to do that. I don't remember what Excel's shortcut key is for zoom in. But if we do 0.8413 minus 0.1587, that looks good. That's 0.6826. That is a number. Like I said, it's kind of a substantial probability. Seems like 50-ish%. Like it's not like, 5%, and it's not like 95%, just visually looking at the picture and seeing how much of the area it covers. So this looks reasonable. Note also that this was one of our claims actually from the empirical normal rule. We have a standard deviation of 1, a mean of 0. This event is all of the outcomes that are within one standard deviation of the mean in a bell curve. Well, the empirical normal rule said that this should be 68%, and we verified that. As an exercise, do these two, right? These should be, say, about 95%. You'll get a couple more decimal places of accuracy, but about 95%. And about 99.7%. Again, you get one more decimal place of accuracy from the table, but confirm that the other two pieces of the empirical normal rule do work. And this is exactly where that rule comes from, that 68, 95, 99.7 rule, being within 1, 2, or 3 standard deviations of the mean for an approximately bell-shaped distribution. And of course, a literally bell-shaped distribution is certainly an approximately bell-shaped distribution. So verify that these work, and then we can actually split our distribution into different pieces. I think we can do this in the last couple minutes here. If I know that there's got to be about 68% total area between -1 and 1, that's about 34% in each from -1 to 0 and from 0 to 1. If I go outside of -3 to 3, that's only 0.3% combined in this tail plus this tail. That's only 0.3%, or like what, 0.15% in each of these tails. So less than 1% there. Outside of 2 standard deviations, so if I were looking at, say, this bigger tail plus this bigger tail, outside of 2 standard deviations from the mean, that should be a total of 5%, the complement of 95%, or that's about 2.5% in either of these cases. And a little bit less than 2.5% in each, because we have to subtract off that 0.15%, but 0.15 is such a small number, I'm not going to write down 2.35%. That's, about 2.5%. And what have I accounted for? I've accounted for 68 plus 5. I've accounted for 73%. I have what, 27% left over then. Call it 26%. So that's about 13 and 13% here. So I can actually use this chart to, look at a, well, sorry, to look at a problem like this one, let's say, and see which areas does it completely cover, or my event completely cover, and which areas does it kind of partially cover, and get an estimate for its size. So when we come back next time, we will pick up with this problem, work through these two as an exercise, and we'll continue on with standard normal distribution next time. Let me stop the recording.